everyone, I'm Zoe. Thanks for getting our startup Visionular's pronunciation right. It's not that easy. So I'm also, I was a colleague of Debugger who gave a great keynote today about AV1, so I don't have to introduce much about this standard. So basically, trying to see this, should I point to somewhere? This one works. Yes, got it, thank you. So today I'm talking mainly about AV1 and commercialized wise, because when we at Google, there's an open source AV1 code base referred to as AOM. So there's still a lot of optimization going on down there. For our team, we're also doing the optimization for the AV1, especially on the encoder size. I'm also we're going to talk about a little bit on the application of machine learning, because everybody talk about it for the encoder optimization. So the first part, let's just talk about how machine learning can be applied to the AV1 encoder optimization. So if you pay attention to the current code base of AV1, the open source code base referred to as AOM, there are already quite some code down there leveraging the use of neural networks, machine learning, to encoder optimization. So roughly, we can categorize the use of machine learning into three classes. So first, to use machine learning for the encoder performance or the BD rate code efficiency optimization. Second is to use machine learning for the encoder speed up. Third, the last, usually people use machine learning to do things like image enhancement, like what Sean has talked about early this morning, so that you can maybe further squeeze down more bits out of the video, and then on the decoder side, you bring that quality back or restore that back to the after the decoder is done. So I will mostly skip up with this introduction of AV1 because Debugger already introduced it. So mainly there are already 42 members on the Alliance of Open Media. We are one of those. And AV1 not only is an open source royalty-free video codec standard, it also shows great code efficiency potential. So this figure, as Debugger also pointed out, was published by Moscow State University. They published the codec comparison report yearly, and we also attended this year's, and the result is expected to come out by the end of August or the beginning of September. But when we talk about AV1, everybody knows it is royalty-free, and it also has a great potential for code efficiency, but the complexity of the encoder is huge. Actually, that's already not the case. And first, we can use machine learning to optimize the encoder. As I mentioned earlier, there's three aspects that we can use machine learning. So the first part, we can use machine learning to speed up the encoder. This is just one of the examples how to leverage the use of machine learning for video encoder optimization in this aspect. So this work was once proposed by Professor Xu in the Beihang University in Beijing. They basically propose the use of machine learning to speed up in the partition decision side. So their scheme is the major contribution I would see in their approach is they can propose the final partition map at the encoder. When we talk about video encoder, there's a lot of partition going on, and it's very time consuming. So their scheme is they collect a lot of data, of course, from the video encoding results, and then train a simple neural network. And finally, when they apply the network for encoding one frame, they can immediately give out the result how this current block can be partitioned. So they refer to it as a partition map. I already organized, besides the use of machine learning for video codec encoder speed up, you can also use the machine learning to increase or improve the code efficiency. And On the left-hand side and right-hand side is mainly, I leave down here is some machine learning scheme that already implemented in the open source, the AOM code base. So if you pay attention and search neural network as a keyword, you should be able to dig out quite some code from their open source code base. And for this one, the third, as I mentioned, you can leverage the use of machine learning to restore or enhance the decoded video quality. So this is another work from Professor Xu. The idea is when we talk about videos, I think some of you also mentioned video is not just a sequence of frames. We want to make sure that the quality across the time domain is consistent. If you look at one specific frame, that quality could be good. But when you look at the flow in the time domain, people's eyes, the human eyes, are more sensitive to the consistency along the time dimension. So this work is mainly to talk about in the video decoded quality, there's some frames that are of better quality, some frames are of worse quality. But using machine learning, we may be able to borrow the good quality frames information and use that to restore those information in the worse quality frames. So the idea here is the first step is to identify in the decoded video which frames are belonging to the peak quality frames or better quality frames, and which frames are belonging to the valley quality frames. And you use 2 subnets to train and finally complete the restoration of the information to the worst quality frames. So the first subnet they use is called motion compensation, and the second one, they finally use the quality enhancement. So from here, the major idea is if you have a good quality frame already present in the videos, you can use the information to get a better quality for other frames. The good thing about this one is to learn something from inside the video itself so that the resulting video can have a better consistent quality across all kinds of different frames. And this one is an effort that we once collaborated with Purdue University for the idea of video analysis of synthesis. The idea behind it is something if we can analyze at the encoder side and proactively remove some information. If we know what kind of things we remove at encoder, we may be able to use machine learning to restore that information at the decoder side. I think this scheme is pretty common. It has been in this area for a long time for video analysis and synthesis. But with the development and involvement of machine learning, we may be able to have a better implementation or installation of such kind of ideas. So this work is one of those. The idea is for those areas in the videos, like we talk about, for example, there's a sports game like a soccer game, and the fields full of grass may be not so important subjective justification-wise. So you could remove those areas and try to restore that at the decoder side. But this specific approach, we basically try to incorporate such idea into the framework of AV1. So in this one, we leverage the coding tool of global motion. So what we did is we borrow the information from the surrounding frames. We only do the video synthesis and analysis on those B frames. Because those B frames, usually they won't be able to be referred much. So if there is a potential artifact that can be propagated from one frame to the other, we can constrain those propagation within 30 frames. This is the thing that I talked about at the beginning. So use analysis and synthesis, we can see a lot of good results on images. But on the other hand, when you look at the video, for example, if one frame full of a like for soccer, like I mentioned earlier, you remove the area of the grass area and you try to synthesize at the decoder side. You may be able to do a very good job for one frame, but if you do such kind of things across all the frames, when you have the video playback, sometimes you see the grass area could be oscillation across frames. That's very distracting. So for this kind of thing, we mainly focus on the use of the synthesis analysis on those B frames. That's the first thing. And secondly is we reuse the global motion coding tool. So what we did is, first, we use machine learning to do a segmentation to identify those insignificant perceptual areas. And for those areas, we specifically to use global motion, because global motion in AV1 is only put the frame-wise global motion parameters on the frame header. And for the block-wise, if it's identified to use global motion, then usually for our scheme, we skip all the residuals. So for that particular block, it not only specified for the use of global motion, all the others information just as coded as a skip mode is completely ignored. So in this information, we can save a lot of bits for coding those areas. But because those areas has been identified as perceptually insignificant area, use global motion, it can be restored in some sense and still maintain a good flow in the time domain. So that's a major idea. Here you can see that we gave some result on the right-hand side that which area has been identified as those areas and has been applied by the use of global motion for implementing basically the idea of video synthesis and analysis. So next, we have just reviewed some of the ideas on the use of machine learning for video encoder optimization. Let's talk about the current status of AV1 encoder and decoder. I think Debug already mentioned that, but he also mentioned that everybody talk about the complexity of AV1 standard. I remember because at the beginning of last year, 2018, January, when MSU Moscow State University first released a report of AV1, it mentioned that AV1 complexity compared to its predecessor VP9 is 2,000 times as complex. But if you look at the current status stating right now is June of 2019, I would say the complexity compared against VP9 is also as low as less than 10 times. So there's a huge progress that has been made by AV1. I personally is a big believer of AV1. So whenever a new standard comes out, there always come out a lot of new tools. Of course, the optimization process is always along the way. So our team is also along that effort. We further optimize the AV1 encoder specifically. But let's first review what is the current status of AV1 encoder and decoder. Debug also mentioned that currently the decoder proposed mainly by VideoLAN and some other partners referred to as David. This decoder has been widely already used in Chrome and some other browsers. It has a very good performance. So these are some of the slides I borrowed from one of the contributors of Mozilla, talking about how David as an AV1 decoder performs compared to other decoders of the state-of-the-art decoders. So the first thing for David 1, when it came out, is actually sponsored by AOM. And the major goal of David is, first, it has to be open source. And secondly, it has to be optimized heavily, particularly for PC architecture and mobile devices. And thirdly, it has to be multi-threaded. That is very important. And lastly, because we mentioned that LibOM is basically still the code base for AV1 that has included almost all, not almost, all the coding tools of AV1. It is still the benchmark for any AV1 implementation. So it requires for any new decoder, it has to be bit-wise accurate compared against the LibOM. So the current AV1, it has all the goals listed down here. And the right-hand side has been giving out the major timelines of the development of David. So you can see that it makes progress along the way. As I mentioned, I gave this, the following results, the credit to Nathan Edge. He, from Mozilla, he gave me all the results. He said, you can go ahead to use all the results that he created. And we just want to spread the word that AV1 from the decoder wise, just use the software solution as a decoder is more or less already ready. That's a major message we want to pass out down here. So the results are here. This is the threading scaling performance by David compared to Libo AOM's decoder, referred to as AOM DEC. Because a lot of people talking about maybe AV1 is not such a standard that is friendly to multi-threading. Actually, that is not the case. So with the increment of the number of threads, you can see that David has been mainly linearly increasing in terms of the decoding speed. And the next figure showing that how David is being performed over iOS devices. So all these are collected over all kinds of different iOS devices. The rightmost one is for the iPad Pro. So you can see that David is able to decode the 1080p videos at the decoder speed of more than 120 frames per second. So from here, you can see that just use the software decoder for AV1 is mainly that for an iOS device, you can decode a 4K video in real time. This is a summary of David. So debugger also mentioned, as I mentioned, so David has already been incorporated to Chrome, actually starting from Chrome 74. Is that to leverage use of David as a decoder, and the other two browsers, including Firework and Edge, all support AV1 decoding. Basically, if you have AV1 coded bitstream, if you put into the browser, it can start to doing the playback. So next, we'll talk about the encoder. This is just one slide. We'll talk about encoder because there's a 3 open source AV1 encoder code base. The first one definitely is the LibOM. So Google is maintained that, but LibOM is such a code base from the beginning, from the birth of AV1. Originally it's from VP10, and then it's actually in the beginning of AOM, back to 2015, it decided to branch out VP9 and become the first version of AV1. And then currently, LibOM is still the benchmark for all the AV1 implementations that has both the encoder and decoder, has all the coding tools still being, I think, fastly optimized along the days. And another 2 AV1 encoder open source solutions, also mentioned by debugger earlier. One is SVT AV1. The other is Ravi. So we got a lot of questions how these 2 open source video encoders are performed. We didn't do it, so we grabbed a community blogger's result and put it down here. So in this figure, these are the results about 3 months ago in February. And from this performance, as you can see that the y-index representing the coding quality measured by using VMAF. Currently, VMAF has been widely used, particularly people who think compared to SIM or PSNR, VMAF is more consistent, aligned with the subjective quality justification. And then the axis is the bit rate. So definitely the higher the curve is, the better RD performance it can achieve. So in this figure, the top 2 curves are from LibOM. One is LibOM 2-pass including encoder solution. The second one is 1-pass. The bottom, the red one, is the 264, the X264 performance. So somewhere in the middle, it has 4 curves. The third from the top in yellow is the X265. There's 3 curves in between intertwined with each other. They basically represent from the result from VP9, SVT AV1, and Ravi. So we would say that as the AV1 implementation, open source solutions, SVT AV1 and Revit are still in the process of being developed. They will catch up someday, but at the current state, they still have a lot more tools from AV1 that has not been implemented yet. So next, the third part, we're going to come out to our own solution. We have an AV1 encoder referred to as Aurora. So how we perform? Our major task is we support the AV1 community. We want to provide the commercial AV1 encoder solutions, mainly for two use cases. The first use case is the video on demand. So basically, I think up to today, all the video on demand, video encoder solutions are in the format of software, because the most important thing for such use cases is coding efficiency. And another one is, all we talk about today is the real-time encoder use cases. So we will talk a little bit of results about how our Aurora encoder performs for these two user cases today. And the first one is for the video on demand use case. We compare our Aurora's encoder against two other state-of-the-art encoders, X264 and X265. We use a very slow speed level from these two encoders because the X265 very slow is widely acknowledged as a benchmark for the video on demand use case. And here we list all the machines we use and command options that we have adopted for X264 and X265. The results are, compared against the X265 very slow, our AV1 encoder achieves about more than 30% speed up for the encoder. And for the coding efficiency-wise, we use both PSNR and VMAP as a quality metric. So we roughly achieve about either 20% or more than 20% coding efficiency, basically the bit rate saving. Compared against X264, very slow, we achieve even better coding efficiency. But again, X264 is very fast, so even against X264 very slow, Aurora's encoder is still not as fast as the speed level of X264 very slow yet. This is the result that we collected over the JCT-VC test set. In this community, I think JCT-VC has been widely acknowledged as a good test set to collect data against. So I believe for the HEVC standardization process, JCT-VC test set has been widely used. So for this test set, the left and right figure give out the results using either PSNR or VMAP as a quality metric. So as you can see that for different resolution, our encoder Aurora has a different bitrate saving performance. But roughly, as you can see from there, that we will say along the increment of video resolution, Aurora usually performs better, or AV1 usually performs better compared against HEVC or H265 and H264. So next, we want to talk a little bit about Aurora's real-time communications. Again, this is still a new standard. And yes, there's a lot of coding tools that has been adopted by AV1 standard. So to make it real-time is still a very challenging task. So what we have achieved by today is we apply Aurora to the lower resolution cases. So we mainly apply Aurora to the full 80p or lower resolution at frame rate of 15 frames per second. But we did achieve a real-time performance request. So here we give out the results how we perform in this scenario. By today, we have already incorporated Aurora into FMPEG for the one-pass CBR scenario. And we give out the sample FMPEG command options. We also already have incorporated Aurora into WebRTC. As of today, WebRTC already, for the RTC community, already gave out the draft how to incorporate AV1 into the RTP standard. However, WebRTC has not officially incorporated AV1 into itself yet. So we basically follow up the RTP draft to incorporate our Aurora inside WebRTC to serve our customer. Here is a figure we compare about the one pass speed. So as opposed to access flow very slow, as we say that we still have not achieved the speed of access flow very slow yet. But for our two-speed level, one's fast and faster, if we can see that applied to 480p, either 15 or 30 frames per second, this is what we talk about the source. Aurora has achieved more than, it can encode more than even 20 or more than 40 frames per second for such scenario. In this case, we can claim that Aurora is more or less ready for the real-time use case. And the next figure, we give out the code, another performance. One is for the one-pass rate control. So we all know that when you do the encoder, the most important thing for the real-time is make the bit rate fit into the bandwidth request. On the other hand, we want to make sure that the bit rate does go flow as steadily as possible. So here we compare our Aurora's encoder rate control result against the x64, the rate control off. So if it stays at the 0% level, that means the bit rate stays exactly at the level of the target bit rate that has been set. So from this figure, we test against more than 10 video sequences along the time and measure the rate control off percentage. From this figure, we would say except one that has too low bit rate, actually our encoder one-pass rate control performs better than access for very slow. Another one, we give out the bit rate saving for this for separate video clips. So more or less, Aurora does show the advantages just by the AV1 standard. So AV1 has so many coding tools. It does have the advantages even applied to the real-time communications. Lastly, so what's next? We talk about our Aurora's use case for both VOD and real-time communication. When we talk about the standard, everybody talk about what could be next, how can we do better? Debug also mentioned the AV2 quarter proposal is on the way. So we talk about machine learning. So what machine learning can be further contribute to the next standard? I just gave out two examples. One is the use of CN for AV1 in-loop filtering. This is a work that has been conducted by a professor in China. And they basically, the idea is, because if you look at AV1, there is, I think Debugger also present a slide along the way to leverage the use of image restoration for the video coding efficiency improvement. So we talk about deblocking, talk about super resolution, we talk about loop restoration, CDEF. So there's a further thing we could do. For example, when we talk about the loop, in-loop filtering, if you can have a I think Sean also mentioned we can use machine learning to do the super resolution. For example, if we have a reference frame, when we do the interpolation filtering, you basically just actually make the resolution to a higher level. So in this stage, the use of super resolution has already shown a great advantages by using deep learning. So in this stage, if you still use the fundamental idea is if you use deep learning, you can get a better interpolated pixel accuracy. So leveraging that, in this work, it shows a better result compared to the current AV1 standard result. So using PSR, you can see that there is a more than 0.2 dB that can be achieved. That's a lot if you achieve even 0.1 dB in terms of PSNR. So this work is along the current way to have a better restoration or interpolation result by use of deep learning. And the next one is another aspect we first talk about. We can add a decoder side to bring back some of the information of those worst quality frames. And this is another work we use machine learning to increase the frame, the multi-frame quality using machine learning. So it also has two different subnets that has been used for the preprocessing, and then it has an easy fusion network. The idea of it is can enhance, is basically categorize the frames into one more category, not only low high, but also it adds one medial layer. So for the 3 different layers, it can bring back the quality of the lower quality frames from those medial frame qualities and from the higher quality frames. And the result also shown that by using such kind of scheme, there's more than 0.2 dB that can be achieved. So lastly, we just want to have a brief introduction of our team. And we are a small team, so we were incorporated in last July. And we have R&D team both here in Silicon Valley and in Hangzhou. I would say our team is an aggregation of codec and machine learning plus image processing teams. So our team, we were pretty proud previously. We have been mainly contributed to the optimization of HEVC, and currently we have been dedicated to the optimization of AV1. At the same time, we also try to use machine learning to do not only to further shrinking size of the videos, but try to bring a better quality to the videos itself. And on the top bottom left figure, it shows that our team in the Hangzhou side, that the AOM first speaker Matt Frost visit our office. And on the right-hand side, we are currently trying to collaborate with including Aurora and some other, especially here, I mentioned the Tutor ABC. They are online education solution providers. They currently already incorporate. So we are on the final stage collaborating with them for the very stage AV1 collaboration. They already try to incorporate our AV1 to replace their current solution. They mainly use 264. So it obviously, they use AV1, they can save more than half of the bit rate that they can compare to their current solution. Here's the timeline. So basically, our goal on the AV1 effort is we try to launch more and further optimize our encoder for the VOD and the live streaming use cases. And for the real-time communications, as I mentioned, we currently only can do on the lower resolution side, but we're on the way to optimize higher resolutions such as 720p and 1080p, which is expected by later part of this summer. We hope we can deliver more real-time solutions for the community. That's it. Thank you.
Does anyone have a question?
Yes.
So all this machine learning algorithm needs some kind of training data on the neural network side. So like if we are talking about a general purpose encoder, how this training data affect, like I can get surely like if you have training data for a particular use case and you run this encoder, it will give fantastic performance. But like how about a general purpose encoder? If you want to have it on mobile or desktop devices, they are not limited to a particular scenario or use case. So in that case, like will it give that kind of performance where they should use as a general purpose encoder, or you have to choose the use case and configure the encoder based on that particular training data and then use it in that way?
Okay, so I think I got your question. That's pretty general, but I can answer your question in 2 aspects. First, as I mentioned, if you look at the use of machine learning in the open source code base, LibAOM, so it has, I think, has incorporated the use of neural network in several aspects to have the AV1 encoder speed up. And for example, in the partition side or in the transform selection, AV1 has, as the debugger mentioned, has 16 transforms altogether. The use of neural network, I would say, if you look at the CL commit message, it always give up the exact figure how much it can speed up. I would say the use of machine learning has bring up at least 100% speed up for just the transform size or even more on the partition size. I would say the speed up of using neural network, here we talk about neural networks or machine learning, not deep learning. So definitely the use of deep learning because neural network itself is pretty complicated. So I would say LibAOM has used usually 1 to 2 layers of neural networks and about 128 nodes in each layer. So that's about that kind of complexity level for the use of machine learning. I think this type of work is very general to be used to any video encoder for speed up. That's one aspect. The second aspect is, as you mentioned, machine learning, yes, because it depends on the training side. So as we are serving quite a few customers, usually our customer strategy is we say, oh, we claim we can do this better. And a customer, the first ones, oh, that's great. Actually, what inside there has, is that true? So usually what they do is they gave us their about like 50 or 100 or even 200 clips. And then we will give back their example. In this process, definitely we are going to look at whether our model really applies to their data set. First, every video is different. Secondly, every customer has different requests. Some, they don't care about much quality. We have some customers look at the video quality side by side. To us, there's a huge difference. To them, there's no much difference. And some other customers, they are very sensitive to the video quality. They like to have a bigger size of video, but they have better quality. In this use case, usually we do sometimes retrain our models to get a better result. Then after we give back the result to our customer, they usually ask for binary or some other kind of test method so that they can apply our encoder solutions to a wider scenario that to their own business purpose. So yes, so that's basically my answer to your question.
When you say you have integrated Aurora into WebRTC, I'm assuming that means like as an internal prototype, or are you planning on like contributing that back to the WebRTC, the open source?
That's another good question. We got a question. First, at this stage, I would say at least within 1 year, we won't be able to open source our solution. And we are a startup. We need to survive. So first, we are still trying to basically license our SDKs or sometimes even provide our own solution. Especially for some of our customers, they don't want to just, we give them SDK. They said we don't have the engineering resources to integrate their solution. So either we provide SDK or we provide our solution. However, we do have the open source in our mind. I would say maybe in 2 years, we will be able to, or maybe faster if our business grows fast. And or AV1 has so well widely accepted. We still have that open source in mind. Yes, we do want to open source our encoder someday. That's for sure.
Hi there. I was wondering, one of your slides had a lot of really great values and bullet points, and at the bottom it said for Apple only. Are a lot of the things that you're talking about just on a specific kind of hardware, or is it generic?
Oh, that's a good question. So that one is specifically I mentioned for David performance. So that's what Nathan, when gave me the slides, he said, unfortunately, he only collect the result on iOS. I think in this community, everyone knows that iOS has a limited number of models. It's always easy to collect results on iOS. Like our solution, we also have another, like just for image enhancement, we have a demo. The one we are trying to collaborate with Lenovo and Vivo. And when we go to there, said, I'm sorry, we only have the iOS demo, but actually all their products depends on Android. So I would say that's like yes, but our solution are for the general purpose use, not only for iOS, but mainly for iOS and Android. Okay.
Thank you.
Thank you.